Li Yu from Tsinghua University in Beijing on artificial atomic spin orbit coupling from modulating gradient magnetic fields.
Thank you, Chairman. I want to thank the program committee for giving me this opportunity to report some of the work in progress. I'm Li Yu from the physics department of Tsinghua University, where one of the wishes we have now is to really build up a strong program in atomic, molecular, and optical physics. So Beijing has become a very cosmopolitan city these days. So if you had opportunities to visit, so I really encouraging junior people looking for jobs that we have quite a few positions. The research in these areas are supported by two umbrella institutes. One is a state key laboratory for low-dimensional quantum physics, which is quantum condensed matter and atomic physics. And we have even larger umbrella institute, which is called the Beijing Collaborative Innovation Center for Quantum Matter. This is between Tsinghua University, that is our university, and the Beijing University, also the Institute of Physics of the Chinese Academy of Sciences. So let me start my talk by thank my group members. So this is a sort of I've been there for 6 years now. We have a group of about 10 graduate students plus, at one time 5 or 6 undergraduate students. So one of the bonuses of working at Tsinghua is we really have very, very good undergraduate students. This guy just went to JQI at Maryland. This guy went to JILA for PhD, and these two guys went to MIT. So each year, we have 5 or 6, and in fact, right now, this year, we have several of them also in Europe, in the best groups in this business. So this, for someone who's been doing theoretical atomic quantum gases for more 20 years, actually this year, right, is about 20 years of atomic boson condensation. So it's really, a pride to show that despite the 20 years of advances in technology, it remains entirely non-trivial to make a boson condensate. This is what we were able to do in 3.5 years. So we make a magneto-optical trap from background rubidium gases in the cell. Then we transport using 13 pairs of anti-Helmholtz coils that are turned on sequentially in time, transported by 50 centimeters or so to this higher vacuum region. Then we do the evaporative cooling and make a boson condensate. Just precisely follow the steps Professor Sergei Hiroshi described yesterday, although the technologies has been completely advanced from more than 20 years ago. The aim is really to study coherent atomic collisions. So when you have gases, atomic gases at such low temperatures, the collisions are coherent. In the absence of dissipation of decoherences, these collisions can come back and force oscillate, and just like unitary dynamics. The specific project we have in mind, this is for the first experiment, is for the rubidium. The lowest hyperfine ground state is F equal to 1. So in a small magnetic field, these are the 3 Zeeman spin components. At such low temperatures, the de Broglie wavelengths for the atoms are microns. Yes, they are significantly larger than interatomic interaction distances, which is a sort of Van der Waals range, which typically is maybe 10 nanometers or so. So if I have 2 atoms prepared in this middle state, they would collide. Because angular momentum and the projection of angular momentum are conserved, they would oscillate 1 to here, 1 to here. This is like energy pooling in typical atomic physics. Yes. For rubidiums, in fact, in the ground state manifold, because at such low temperatures, the interaction is insensitive to the details, so you only need 1 parameter. But this is, which is a scattering length, for rubidium is F equal to 1, so you actually need 2 parameters. 2 F equal to 1 atoms could collide with S waves in symmetric channels of total spin equal to 0 and total spin equal to 2. Rubidium was the first element to both condense because it's a good species of atoms in the sense that these two numbers are very approximately the same. So that means most of the interactions are density dependent, which is much, much larger than spin exchange interaction, which is the difference between these two numbers. So that means the density dependent interaction is more than 500 times larger than the spin exchange interaction. That means if we make this condensate confine a small well, small harmonic trap, that means their shape, the mode, the spatial mode of the condensate would effectively remain the same, but these collisions, oscillations would come back and forth. This is the so-called quantum spin mixing. So I can describe this dynamics using a one-dimensional Schrödinger equation in these spaces, which labels the number of particles in these three spin components because the spatial wave function are the same. If I were able to start with all atoms in this state, then the superposition would correspond to pairs of atoms, one pair, two pair, three pair, and etc. Yeah, then let me turn on the dynamic simulation of this one-dimensional Schrödinger equation. You see, you have many, many amplitudes come into play because it's a coherent superposition. So these would be the semi-classical behavior shown in the oscillations, but these noises, they are not technical noises. They are really fundamental quantum noises. Now, at this point, I come to this story yesterday was told by Professor Harosh. He said a coherent state is a state where the photons share all the same phase. But in fact, the coherent state, if you look in the time domain, the photons are completely random. It's not much different from the microwaves your microwave would generate. So these noises are quantum noises in the sense that when you have these superpositions, if you make a measurement, you collapse into different superpositions. So these noises actually limit the ultimate sensitivities of an atom interferometer. So one of the aims that we have is really to try to beat these noises. In the collision process I just described, although the number of pairs shows up as almost like a coherent distribution, but the number of atoms here and here should be identically the same. That means they always come out in pairs. That means the relative number difference is a non-fluctuating number. That means completely squeezed. So this is what actually we were able to see. That although these oscillations don't look like very sinusoidal or very smooth, but if you look carefully, the plus and minus components, they always come out exactly the same. In fact, the ability to make a claim of how much squeezing we are getting is now limited by our imaging system. That means the number resolution of atoms we can get. Currently, we are limited about 40 atoms, so that means we can maybe get 5 dB or 6 dB. But this is a hotly contested field. Many groups are involved in doing that. The best now we can do is, in this business, people can actually get to like a 10 dB suppression of the quantum noises in those oscillations I show you. That means the so-called quantum shot noise of the 90% of that is being suppressed through this mechanism. That this is, in fact, ongoing. We hope by the end of the summer we should be getting to there. If you are familiar with this, this is what we call the SU11 interferometry. So now I come to the announced talk that in the program, which I will be describing artificial spin orbital coupling from gradient magnetic field. This is a collaboration with a colleague of mine from the Institute of Physics. So these other topics are also relevant, in particular this last one. If we can generate this artificial spin orbital coupling, we can look at what the effects are on the ultra-cold atomic collisions. In fact, you will find the richnesses never before existed in this regime. That means the Wigner's threshold laws will be completely modified. So for this work, there's already a preprint in the archive. And also in the recent DEMAP meeting, we announced some of the new results, which I will also be saying a little bit here. So what is spin orbital coupling in cold atoms? This is not the usual spin orbital coupling which gives rise to the fine structure constant in atomic structures. What we are talking about here is aimed at simulating spin orbital coupling in quantum condensed matter system. We know in the crystal, in the metal, the electrons, when they move, the electric field from the nuclei they see would turn into the magnetic field, which then couple to the spin of the electron. So there are two general types. One is called the rush bar, the other is called the dress houses. Within quantum condensed matter physics, it's understood that spin orbital coupling of these types are very important for the interesting phenomena like spin Hall effect, topological insulator, or spintronics. If these particles are fermions, also spin 1/2 fermions. But in cold or ultra-cold atomic gases, we could go beyond the spin 1/2 particles. What I will be discussing here today is for spin 1 atoms. So it's a boson. So people always ask me, what's used for it? In fact, I don't know. But for me, I can only do what I can do. In fact, spin orbital coupling bosons, it turns out it's a type of quantum matter never before existed. So this is a dispersion curve of a free atom in space, in free space. Yes, it's a p²/2. So in this sense, the spin orbital coupling, a particular type we are trying to synthesize, simply shifts the momentum by a spin-dependent amount, which is equal to an equal superposition of these two types. So then dispersion curve becomes this red and blue. They shifted along this direction of spin orbital coupling. So you notice here there's a Dirac cone. If you have any interest in quantum condensed matter, you know this is a nice feature many people would be excited about. This idea, or this type of interaction, was first realized by the JQI group of in Spielman. In fact, in 2011, they realized the effective interaction using Raman scheme, again with rubidium atoms in the F=1 ground manifold. They turn on a small weak magnetic field because of the second order quadratic Zeeman shift. They can make this two-photon resonance to be different from that. So selecting these as spin up and spin down for pseudo spin 1/2 bosons, they can Raman couple them using two Raman beams that are counter-propagating. That means this transition will be momentum sensitive by the recoil momentum of these two photons. This now is really an active field now. I think more than 10 groups are actually involved in doing that. A lot of groups, including from within China. So this can be really very well understood if you know so-called dark state cooling from early days of the laser cooling, where Alan Icpeac had this idea that if you have two ground states which are connected to the same excited state, there's an equal superposition between these two ground states, which is not coupled to the excited state. This superposition is called the dark state. The dark state is only dark, completely dark, when its momentum is 0. If its momentum is not 0, it will be coupled to the bright state. Then there's another possibility of getting optical pumped to the dark state. So if you look at this transformation of this, it's just the same as a momentum shifting operator by a spin-dependent amount. So this is identical the same mechanism for used in the Raman beam to generate spin orbital coupling. So when we realized that in 2012, we wrote a paper. We said that there's a more general way of doing that. If you apply a gradient magnetic field in one direction, then the three Zeeman components would be experiencing different forces. If you pulse this on, that means let this force integrate for a certain amount of time, then the three spin components will be getting different momentum impulses, exactly like in the Stern-Gerlach effect. So that means, for instance, this one would be getting a momentum impulse that direction, this would be coming to this direction. Now, if you turn on two pulses of opposite amplitude but separated by a duration of free evolution, this approach is exactly the same as a momentum-dependent spin shift, and hence you can generate spin orbital coupling. Well, this idea can be also generalized instead of using pulsed scheme, you can use a modulating scheme. A modulating gradient magnetic field, if it turns out, is much better because in the pulsed scheme, if you want to do it at a very short pulse limit, then the eddy currents and the magnetic fluctuations really become a problem. So then you can generate this type of interaction. And as showed in the paper by Spearman and his collaborators. So this is what we do in a single chamber atomic Bose-Anderson condensate experiment. So we have a pair of anti-homohost coils which generates a three-dimensional quadrupole magnetic field. Then outside we have this bias field. The bias field selects out, if this bias field is large, for instance at 5.7 Gauss, which is typical value we use, then selects out one-dimensional gradient magnetic field, because otherwise it cannot exist because its divergence is not zero. Yes, you have to include this bias. Then we're modulating this gradient magnetic field by modulating the current here. The Bose-Einstein condensate is here, then we can try to implement our scheme. This is actually the real experimental setup. If you are not familiar with that, this is a single chamber atomic Bose-Einstein condensate, which is made somewhere lower. Then we use three pairs of anti-homo coils to move the condensate up close to the edges where we can apply gradient magnetic field even at a distance which is rather far away. In fact, we are now actually limited by the strength of the gradient we could apply. So we first decided to do a Ramsey interferometry with gradient magnetic field pulses. So what is Ramsey interferometry? Yesterday, Professor Hiroshi explained this. You apply a pi/2 pulses, wait some time, then apply another pi/2 pulses. If we start from a polarized state, in one of the spin states, we have to add first pi/2, yes? And then we can add this magnetic field scheme. So if we do that, we, in fact, is working with f equal to 1. So that means we have a 3-spin component, Ramsey interferometry. And let's see what will happen. This is what we see. That we see that, indeed, the fringes show up in these different spin components. That means we were indeed able to use short magnetic gradient pulses to impart spin-dependent momentums to this condensate. If you check these fringe spaces, it really agrees with the theory, no problem. Yeah. So this actually by itself was very interesting. Initially, we didn't notice that. Then Ron Foreman was visiting us. He said, hey, you guys just did a Humpty Dumpty interferometer. Stern-Gerlach interferometer was previously considered impossible to do because in the Stern-Gerlach experiment, the spin atom comes in, yes, it gets split into 2 spin components. If you want to connect another Stern-Gerlach magnetic gradient in the opposite sequence, trying to make an interferometry, this is very difficult to do because usually the atoms you are dealing with here doesn't have enough coherence length. So then it's like in the Humpty Dumpty experiment, when you break it, it's very difficult to put them back together. But in fact, we just showed you that we can do that, yes? So now let's see what happens if we really apply this pulse sequence to do this, to synthesize the spin orbital coupling. So this is for suddenly turn on. I suddenly turn on these periodic modulations. Let's see what the atoms are doing, yes? So we would expect when we suddenly turn on, if the atoms are in the superposition of 3 spin components, their different spin components will follow their different dispersions. So that means for the -1, +1 spin component, they will be offset. And the atoms are always located here, so they would start to oscillate in their dispersion curves. In fact, this is indeed what we see. Using the time of flight measurement, that means that we apply this sequence, then we turn the sequence off, then let the condensate expand for some time, then we take the snapshot. This is indeed actually what we see. If you look carefully, in fact, we found that we also excite the quadrupole mode oscillations of the condensate as well. But overall, this agreement is really perfect. Now we also try to see if we can turn this adiabatically on. This is what we do, that we adiabatically turn this on, and then let's see what we would expect for the dispersion curves. So the atoms in their dispersion minimums will then follow the minimum. And this, again, is indeed what we see. There are some residual oscillations which we are trying to understand. But overall, this agreement is pretty good. So this shows that the idea of using pure magnetic gradient field to generate spin-orbital coupling seems to be workable. In fact, people always say, well, why don't you use lasers to do these spin-orbital coupling? Many groups have tried, and they seem to work beautifully. Well, lasers indeed can cool atoms and control atoms, but as also explained by Professor Harushi yesterday. In fact, cold atoms and lasers are, in some sense, enemies. When you have a spontaneous emission, the extra energy released would be just destroy your coherence of the condensate. And in the Raman scheme, as I described, first suggested by and implemented in the Spearman group, spontaneous emission is a serious concern. But in the particular case of the two pseudo-spin states being the same Zeeman component of alkali atom, the two photon transitions do not couple to the nuclear degrees of freedom. Yes? So that means in order to flip the nuclear spin in the pseudo-spin manifold, somehow you have to use the excited state. That means fine structure in the excited state. So that limits the detuning you would have, and also limits the ability you could try to counter atomic spontaneous emission by turning to large detunings. So purely magnetic means that has its own advantages. Now, recently, we come out with this new idea together with Masashiro Ueda. So we said, well, these atoms are trapped in the condensate. If your modulation frequency trapped in the harmonic trap, yes, if you can modulate your gradient magnetic field close to the frequencies of the trap, maybe there would be enhancement. In fact, we immediately worked out a theory, and this is a measurement. Yes, we found the strength, that is to say the momentum you can impart to the atoms indeed is frequency dependent. So the strength of the spin orbital coupling synthesized has this really nice resonance curves. When you are at very high modulation frequencies, it's fixed. But when you tune close to your trap resonances, it shows that there's a pi phase shift, also the resonance behavior. And this is also, again, completely verified in the experiment. So what about atomic loss? When you are trying to modulate these things or kicking, shaking these atoms using a magnetic field, it turns out that they are acceptable, certainly for spin orbital coupling experiments. That means intended to try to observe amenable effects. When we have a single component condensate, two component condensate, or all three components with atoms in, we find that in order to reach a momentum kick of the order of 1 photon recoil, the lifetime actually is sufficient for performing most of the intended experiment. We can also work at lower densities here with all three components included, and with 290 millisecond coherence times, and reach a recoil which is very close to what they can do in the Raman-based scheme. So what about the heating? In fact, there is indeed a heating observed. But again, this seems to be quite reasonable. That is when you are modulating, driving at frequencies which are sort of not exactly on the resonance, but at 2 or 3 times, where you could reach an enhancement of factor 2 or 3, but still the heating is acceptable. So now, the spin orbital coupling I just described is simply a spin-dependent momentum shift. This seems to be that it can be gauged away. That means that you make a gauge transformation, that it seems to disappear. That is indeed true. But in fact, if you add another sequence, that means at another interval where you're directly doing RF coupling, then you can solve this problem. This idea was first suggested by Klaus Schenstock's group. And we can also try to generalize this to more than one spatial dimensions, which is, this is now one of the really the target everybody is trying to get to is that we can do this pulsed scheme in X direction, then in Y direction, then you concatenate them together. As long as the actions from each of these intervals is small, then the effective Hamiltonians simply add up together. I think my time is coming close to the end, so let me summarize what I reported. So first, we have been able to synthesize one-dimensional spin-orbital coupling for spin-1 atoms. This is not previously known in quantum condensed matter physics. The main advantage of the purely magnetic scheme is continuously tunable. So I enhance the gradient magnetic field amplitude or make the pulse slightly larger, then I can tune the spin-orbital coupling strength. This is also not limited by atomic spontaneous emission. The modulation loss and heating seems to be acceptable, and we also find that using trap resonances, this can be enhanced. In the future, we want to do direct coupling between the spin state and also try to see if we can do this in the optical lattices. But just a few weeks ago, I realized that Esslinger's group already implemented this in the magnetic lattice. We are now also currently trying to generalize this to 2D. So I will stop here. Thank you for your attention. Yeah.